Okay, here is my working on this practice quiz. And remember that the big idea is that with this concept is we're trying to find the area underneath this curve, this graph, and the x-axis. And that's called integration. To do that, to get an approximation of that, we could draw a trapezoid underneath, or using the curve as kind of the basis for that. And when we do that, we end up with kind of trapezoid turned on its side, and here would be like the top base, and here's the bottom base. And we would consider this lower area the height between 0 and 2. And that approximation is going to be higher than the actual area because this trapezoid is bigger than the space below the red curve. And so use the area of a trapezoid, 1/2 base 1 plus base 2 times height. To get base 1, you input x equals 0 into the function, and the y value is the point. It's the height of the trapezoid, the base 1, excuse me, at that point. And then input the f of 2. So put 2 into 1/6 x cubed plus 1, and that turns into 2.33. So the base 2 there has a length of 2.33. The height is 2, and then I just plug those in. Area equals 1/2 of the two bases added times the height, 2, and then multiply 2 and 1/2 that cancel each other. So I end up with I end up with just the two bases being added together, which is about 3.333 units cubed. Now, another way for us to do this, to estimate the area of the function, is to use rectangles. Now, I've kind of drawn in here green rectangles, and those green rectangles, kind of right in this, well, that's not green, so that's not helpful, but are a little bit underneath the red curve, and there's 4 of them. And I'm using kind of the left-hand bases in this case, and I kept it with bases just to keep the kind of the consistency of how we're doing this. And I want to make 4 of those lower rectangles. And so rectangles are base times height. So it's the first base times height plus the second base times the height plus the third, et cetera, et cetera. And so algebraically, they each have a height. So I'm just going to pull out the height, factor it out, and add up the bases. And I used Desmos, and I recommend that for you too. Write in the function and then click on the table section. So then I don't have to do all those calculations. And I end up with all the bases, okay? And I'm adding, there's 4 of them in the first problem because I'm asked to make 4 bases or rectangles. And then I also need to look at the upper rectangles, and those are the blue ones that are kind of scribbled on there. And the blue ones are using kind of the right-hand side of the bases, including the very one to the far right, the tallest one there. And so I'm doing the same thing, and the height of each of these is this length right here, 0.5, because there's four rectangles exist between 0 and 2. Each of them have to be 1/2. And then I'm adding up those bases. Now you can have Desmos do this cool thing for you. If you define the function, if you would write, if you put into Desmos f of x equals 1/6 x to the third plus 1, well, I can have Desmos do all the calculations of the bases, or that dimension of the rectangle. So I can take the height times the left-hand base, the 4 of all those bases. Okay. So that's about 2.375. That would be the lower area estimate. And then I did the same thing. I just copied and pasted that in there, but added this, the far right rectangle, and took out the first one. And so I had Desmos do that work for me. And then I summed up all the areas, multiplied by the height, and I ended up with 3.0416. So that's my cat in the background. So my daughter's cat. So then that's what the lower one went there, the upper one went there, and then I averaged those two. I added those two up and divided by 2 in order to get that estimate of the area with rectangles. Now we get an even better estimate if we use more increments. In this case, 10. So between 0 and 2, I used 10 increments. So I basically took 2 divided by 10 and got 0.2 is each height. essentially. And then I'm going to do 10 different rectangles using the left hand and the right hand in this case. So again, I use decimals, and I made this big table, and I typed in the increment 0, 0.2, 0.4, etc., etc. And then I had Desmos calculate the lower area by, what you don't see here, because there are 10 of them, is the height times then this first, second, third, fourth, etc., rectangle. And then I did it again for the upper. So I took these 10 bases times the height, summed them up, and I ended up with two different values, about 2.54 and about 2.807 for the upper area. Average them, and I get about 2.6735. Now let's look at the antiderivatives. And so the process here is with a polynomial type function is we increase the exponent by 1, which is often called n plus 1. So I make that 4. But to counteract that, when I do the opposite process, I need to divide by 4 or multiply by 1/4. So that needs to factor into the first piece. And then the second part of that polynomial, the 1, well, that's like x to the 0. So that's going to increase by 1 to make it x to the first, and then divide by 1, which doesn't really change it. But so what I end up with then, to make this work, is I have my original 1/6, then I multiply by my 1/4 to counteract when I do the power rule to make 1/24 x to the 4th plus x, and then I added my constant of integration because it does not matter what number that is. We want to recognize that there's an infinite number of functions that could be the antiderivative. Now, what I would recommend you do is check your work. So take the derivative of the function, the result you found, and see if it turns into the original. So, or the derivative that you're given. So what I did is then I took 4 times a 1/24, x dropped the exponent 1 to the third, and 4 over 24 makes 1/6. And I have plus 1 when I do the derivative of x. So what I end up with is 1/6 x to the third plus 1, which is what we started with. On the next one, we have to consider the chain rule in this one, because this piece, the 16x, is a function within a function. And also, a challenge here is to recognize that to get sine, I have to have negative cosine to start out, because the derivative of cosine is negative sine, so I need to get that negative in there to counteract it. It's kind of what we're doing here. Okay, and also there's a u piece, so there's going to be with the derivative a times 16, because the derivative of 16x is 16. So to counteract that, I'm going to use this 1/16 in this case. So I'll take -4 times 1/16, and which reduces to, or becomes -4/16, which becomes -1/4. And then I have the cosine, and then the 16x, I put the u back in, and then plus the constant of integration. Check it. Do the derivative. So I have -1/4 cosine of something, and that something is 16x. That means I'm going to have 1/4 sine of 16x, and then I multiply, the chain rule says we multiply the derivatives, times 16, and 16 times 1/4 is 4 sine 16x. On to the last, which is essentially, I'm looking at like something to the 15th. So to work backwards, this now needs to become to the 16th, and to counteract that, I need to get in there a times 1/16. Okay, so I'm going to have, so I put the u piece back now, I'm going to have -8x minus 10 to the 16th, and again times 1/16. And then I need to consider, though, this u, because its derivative will also factor in to the process, and that is -8. So to counteract -8 being multiplied by the function when I do the derivative, I'm going to have to get in there a times 1 over negative 8. So then combining those, I'm going to have this really kind of not so pretty fraction, but if I do my math right in my head, it looks like 16 times 8 should be 80 plus 48. It's 128 and negative. I have negative 8x minus 10 to the 16th. Okay, so check. Take the derivative of that, and it should turn in to the original problem. Okay, negative 8. Let's make this the u, and u is negative 8x minus 10. Okay, so then the derivative is 16 times negative 1 over 128. Replace the u, since I'm done with it. Reduce the exponent, and multiply by u prime. So then 16 times negative 8 is negative 128. Times negative 1 makes a positive 128 over 128 times negative 8x minus 10 to the 15th. And then, of course, this is 1, which is what we started with. Check, or what we wanted to get. So the process again is kind of undoing, working backwards, thinking what you're going to have to do the derivative, and then trying to do the reciprocal of that so it disappears. And I hope that you don't disappear. Talk to you later. Good luck on this tomorrow, or whenever you take this assessment.